Hello everybody, and welcome back to part 5, the final part of this video series, where today we're going to be answering the question using the Maxwell construction, plot the two-phase envelope superimposed on the PV isotherms of part 3. Excuse me. And let's break down this question, okay, using the Maxwell construction. Okay, what's the Maxwell construction? Well, if you Google the Maxwell construction and go to Wikipedia, this is what you get. This is the Maxwell construction, okay, where you have a PV diagram and then an isotherm, right, and then some pressure that can move up or down, right? But the thing that's special about the Maxwell construction is that this area is equal to that area, okay, and then when that is true, when that line makes this area equal to that area, that P is actually the vapor pressure, okay. So let's move into Python and get started with this, okay. So first things first, we talked about integrals, okay? So first thing we want to do is talk about how we solve integrals in Python, and you can do that two ways. You can do that with an explicit closed form solution that you find on Wolfram Alpha, or dare even, hand solve a closed form integral. But I don't really want to do that, so we're going to be using a numerical method, and that numerical method is from our favorite Python package SciPy. So from SciPy.integrate import quad. It stands for quadrature. It's a numerical method of solving integrals. Okay. So then we also want to import SciPy.optimize import root. And the reason we want to import root is, well, we're gonna tell Python to essentially make guesses, a whole bunch of different guesses for P, then go up or down to make the Maxwell construction too, where this area equals that area. Okay, so let's not get ahead of ourselves. I'm just explaining why we want root. But the first thing we want to do is sorry, I'm trying to type and think at the same time, which I really shouldn't do. We want to define our integrals. We want to make a function for our integrals, a function for the actual root function to make guesses in. I feel like I said function way too many times, but okay. So we're going to call it Maxwell areas, area 1 and area 2, right? And we're going to think about what it wants to take in, okay? So we know it wants to take in P because we're making a guess for our pressure, but what else is Maxwell's areas defined upon? Well, we know we're going to be using cubic V to find the roots. The cubic V roots are our limits of integration, okay? So we also know it wants to take in T. Does it want anything else? Well, let's look at what else do we want to use. We want to find out this isotherm, so we're going to be using cubic P, right? What does cubic P want? Oh, it wants V and T. But we already get V from cubic V, so that's all the arguments it takes. Okay? Next, we want to define another function that is in our integrand. In other words, we want to define a function that is the inside of our integral, right? So it's like the integral from v1 to v2 of P minus our function cubic P, okay? The inside of our integral. So integrand, what does it take in? Well, once again, it takes in P and T, right? I believe it also, sorry, I'm having a bit of a brain fart. I don't think you need to define V if it is already defined outside of the function. Okay? Oh dear. I should mute WhatsApp when I'm recording. That was my brother. Okay, getting off topic here. Integrand. What's inside the integrand? Well, I mentioned it. It's P. Think back to calculus 1, how to find the area between the curves. It's the function P, okay, minus the cubic P. So P, I would guess P, minus cubic underscore P. Is that how I named it? Yes, lowercase c, uppercase P, and it wants to take in V and T. Okay, and we're returning this. Return. Okay, and let's get our roots, our limits of integration ready. V1 v2, v3. Remember, this is v1, v2, v3, and that we get that by using our cubic v function that we just defined, right? Equals, we're unpacking it, cubic underscore v of p and t. Okay, and then finally we want to make the Maxwell areas return something. Okay, and this is where quad comes in. Quad. Okay, let's take a look at quad. Return quad. What does quad want? Quad wants a function, a, b, lower limit of integration, upper limit of integration, and a whole bunch of other things that we, for our context, do not care about. So function. What's our function? Well, our functions are integrand. So integrand. Okay, lower bound. Oh, what's our lower bound for the first area? Is v1, v2. v1, v2. Okay, and the thing about quad is that it returns an array. It returns a two-dimensional. I'm going to rephrase that. It returns an array of size 2. Okay, where the first element is, the actual numerical evaluation of our integral, and the second element is our error. Okay, we don't care about the error in the context of this class, in the context of this problem. We just care about the numerical evaluation. So therefore, we can tell Python that, hey, I only want position 1 of that array. Okay, and we do it one more time, right, to get this area, and we change the limits of integration to v2 to v3. Okay. So next thing we want to do is to create our function that the scipy.root is actually making guesses in. Okay, so we'll call this define. What will we call this? We'll call this area underscore diff. Okay, and once again, you can see that it's already been defined because, as always, this is not the first time I've attempted recording this video. Okay, so that's besides the point. So what's it gonna take in? Well, recall that the way that the scipy.root function works is that it always has, in the first argument, our vector of guesses. But in this case, it's a vector of size 1, okay? Because we're really only guessing what p is. And the other thing that's required for the operation of Maxwell underscore areas is t. So without further ado, let's get into it. Okay, we need to define p. P is equal to the first position in the vector of guesses, the first position in a vector of size 1, but we need to do it anyway because that's how Python wants it. Okay, and then we need to define what area 1 and area 2 is. Okay, so area 1, area 2, we're unpacking this, the export, the return, we're unpacking the return statement of Maxwell areas equals Maxwell underscore areas p and t. Okay, next we want to return the difference between these two areas, right? But look at over here. This is a negative area, and this is a positive area. So rather than doing area 1 minus area 2, we can just do area 1 plus area 2, okay? And there you go. That's our area difference function, and that's the function that the function that scipy.root will make different guesses for p, right? It's going to guess this p, moving it up and down until this area equals that area. Simple as that. Okay, so at this point we have all of our necessary functions prepared, so we can start thinking about plotting. So let's start setting up some arrays where we can throw data into to plot. So that's going to start with a VG list for the gas, the vapor, and then same for the liquid, right? Okay, and that's our x-axis, and we need to also consider our y-axis. So what's our y-axis? P vapor. Okay, so these are all lists that we need to define. Okay, and we're going to plot this envelope by calculating the vapor pressure for various temperatures over and over and over again. So what does that sound like? Well, that sounds like we need to use a for loop to iterate across different kinds of different temperatures and just recalculate the vapor pressure, right? So, but there is one small issue, and that is, well, as we get closer and closer to the critical temperature, we actually want to take smaller and smaller steps. But how do we do that? Well, we can do that using math, right? Math is an amazing thing because we can talk about it and manipulate a function in order to get that function to model what we want. So again, we want to get our temperature, right, to take smaller and smaller and smaller steps as it approaches the critical temperature. So how do we do that? Well, think about math and some different mathematical functions, okay? So what does that sound like? That behavior sounds like an asymptote, right? Where an asymptote, gets closer to and closer to a value, right? And it gets infinitesimally close, and it takes smaller and smaller steps as it gets closer, but it never actually touches it. Okay? So let's think of some functions that exhibits that behavior. So in this case, we're going to be using e to the x. Look at that. And that asymptote is 0. It approaches 0 as x becomes infinitely negative, right? But let's start manipulating this equation to fit our purposes. And first and foremost, our temperature isn't going infinitely negative, it's going positive, right? Growing positive. And here's another problem. It's approaching 0. We don't want it to approach 0. We want it to approach some number. And if you do 1 minus e to the x, then, 1 minus e to the negative x, then it'll approach the number 1. Okay, look at that. So we now have a function that starts at 0, right? And then it'll approach 1. So we can start manipulating this. We can actually multiply it by a constant, and that constant will be whatever the number that will approach, and we can therefore multiply it by the critical temperature, right? But there's one more issue. We don't want it to start at 0, because what's happening at very low temperatures in Kelvin, right? You're gonna have a solid. You're not gonna have a liquid or a vapor. You're gonna have a solid. So you actually want to offset the whole function by something like 270 Kelvin. So then, it's guaranteed that you have a liquid or a gas. So now you have a function that's starting at 270 and then approaching some constant. And again, that constant is going to be the critical temperature. But there's one more problem. It's going to now approach the critical temperature plus 270. So how do we fix that? We can fix that by, well, let me illustrate it in Python. So let's start with the for loop. So for x in, we'll do linearly spaced points from 0 to like 7 and take 500 points in between. Okay, and we're going to say t equals start with, let's see, 1 minus np dot x negative x, right? And plus 270, okay? And we're going to multiply it by the critical temperature, P dot Tc. Okay, and back to what I was saying before I stopped my thought. Right now, what this function is modeling is it's saying that, okay, we're going to start at 270, and we're going to take smaller and smaller steps as we approach the critical temperature plus 270, right? That's wrong. We do not want that. We want it to approach just the critical temperature. So the way to deal with that is subtract 270. There we go. And now we have a function that will start at 270, and it will approach the critical temperature, never actually reaching it, and then it takes smaller and smaller steps as it approaches it. Okay, so let's move forward with calculating the rest of our plotting terms. Okay, so first and foremost, we want to determine the vapor pressure, right? And recall that the vapor pressure is, that pressure that makes the Maxwell construction true. In other words, Pvap is equal to, and we're using the root function to find that pressure, right? So root, what does root want? Root wants a function to take guesses in, and that function is area underscore diff. Okay, what's the next term that root wants? Well, root wants something it wants some guess in a vectorized form. Okay, and we're gonna initially set the guess to something like 100. Okay. Well, there's one more thing that we haven't seen before, is that area diff actually takes in 2 components, and it is only guessing one component. The other component stays constant for the context of that iteration of the for loop. So the way that the root function deals with that is it takes in args equals t, right? So now it's saying that, okay, the second argument is equal to t. T is calculated here, and it's not going to guess that. It's actually going to guess. It's going to guess pressure to see what pressure makes the Maxwell construction valid. Okay. I believe that's all that's needed for the root function. But then again, remember that the root function actually returns a whole dictionary. We do not want that whole dictionary. We just want the number that it decides is, okay, this is the value of p that works for this, and it returns it as a vector once again. Okay. And then there's one more issue. One more issue is that every time t changes, the vapor pressure changes as temperature changes, right? So how do we deal with that? If the vapor pressure keeps changing, then our guess is going to be inaccurate. Well, you know, it's as easy as setting our guess equal to Pvap. In other words, every time this for loop iterates, it calculates the vapor pressure, okay, based on an initial guess, and then it says, okay, my next guess is going to be that vapor pressure. Okay, and this is the reason why we want so many points, because if there's not enough points, then the steps are too far away, and the guess is inaccurate for the next iteration. Okay, so let's really quick check the functionality of our function. Yes, no errors, which is good. And I'll show you what happens if you have 2 large steps. If you have 2 large steps, each guess will be inaccurate, right? Therefore, causing the Cardano's equation to only return one root, which, you know, kind of breaks everything, which is why it's super unhappy here. So change it back to 500. The steps are small enough so that the previous vapor pressure is good enough of a guess for the root function to work, and everyone's happy, right? Python's happy, I'm happy that it's working. Okay, so what's next? Well, we want to determine our volume of the gas phase and volume of the liquid phase, right? So how do we do that? We do that with the function cubic v. So cubic v, if I can type, cubic v, what does it want? It wants p and t. Well, we have that, Pvap and t. Okay, but what's it equal to? So it's equal to, it changes, it sets it in order, right? Because that's the way we designed the function. We told it to, well, design the cube roots, and we told it to sort the roots in order, right? So if the specific volume is in order from lowest to highest, then that tells us, okay, the lowest specific volume is it correlates to the specific volume of the liquid, right? Because liquids have a smaller specific volume than vapors. So we can say that, okay, VL, and then the middle root is trash, right? And we don't care about it. It doesn't mean anything. And it's common convention in Python to call that trash variable underscore, right? Because underscore is a perfectly acceptable variable name. You can throw it in the trash can. Next up is the volume of the gas phase, okay? So we've unpacked that right there, okay? And then next, inside the for loop, we want to append each value to each list. So vg underscore list dot append vg, okay? Then vl underscore list dot append vl, right? And finally pvap underscore list dot append pvap. I believe that is all correct. Okay. Let that run, make sure we don't have any errors, we're all a-okay. But then you're starting to wonder, okay, we want to plot it, but look, we have three arrays. So how are we going to deal with that? Well, we can smush these arrays together, right? Remember numpy from W3 schools. So we're going to call this we'll call this vplot, v volume for plotting purposes, equals, we're going to start with the liquid on the left because it's the smaller specific volume. So vl list plus, so if you, I don't know if that's the right operation. I don't know if that's the right operation to I think the vocabulary is concatenate lists. So let's look it up. Python, how to concatenate lists. Okay, I don't know if it's just a simple addition operator, or you have to do something fancy. Well, let's try it and we'll see what happens. We'll know if we're wrong or not, right? So vl list plus vg underscore list. Okay. But the vg list is actually iterating from the left to right, right? We don't want that. We want it to iterate from right to left. So the way that we reverse that, I said one thing and I meant the other. The VG list, as it's calculating in the for loop, is actually iterating from, now imagine the graph, right? It's iterating from the right-hand side to the left-hand side. We do not want that. In order to connect these, we want it to go from the left-hand side to the right-hand side. So we need to reverse this list, and the way we do that is we say, okay, we want these two columns to be the same, and then reverse the order, right? So let's check that. Should be good. And I'll get vprint v underscore plot so we can take a peek at it, see what's going on in there. Well, you know what? I don't think I can. I don't think I have enough foresight to tell whether or not that's good. So we'll continue. We'll continue and we'll figure out whether or not it's good during the plotting phase, right? So vvap underscore list equals pvap underscore list, and it's the same thing, right? But we also want the pvap values to correlate nicely to the vg values. So we do the same thing, vvap underscore list, and reverse the order. Okay. And let's go ahead and plot it. We can plot it by, we can just take our function from earlier because we want to superimpose it, right? And we'll call this fig2 as to not confuse Python. To call it give this object a different name, and then we'll add this. We'll add another scatter. Oh, we don't want it inside the for loop though. We don't want it to iterate a bunch of times. And we'll x is equal to v underscore plot, right? And I did not want to call that. I wanted to call it p underscore plot. And y is equal to p underscore plot, right? Okay, and we'll make this mode equals lines. And then we'll make it easily visible, we'll do line underscore color equals white. Okay, pplot is not defined. That's because I didn't run it. Okay, good. I was right. The plus operator concatenates the list. I don't know if I'm saying that word correctly or not, but okay, look at that. We have our vapor liquid envelope plotted very nicely here. And you'll notice that, you'll know if you have a bad plot or not by if you zoom in here, you'll you would see a straight line straight across, right? And that's because you're not taking enough little steps closer to the critical temperature. See this critical temperature isotherm? If you didn't take enough little steps, then it would not get close enough, and it would just shoot straight across horizontally, right? And with this concludes part 5 of the video, and it concludes the series. Thank you, and I'll see you next time.